All right. Welcome. My name is Raniz. I am a coding architect at Factor 10. I've been doing software for, I've been getting paid to do the software for almost 20 years now. And when I can, I'd like to make software do software for me, so I don't have to do it myself. And that's what I'm going to talk about to you about today, which is compile time code generation in C#. And basically, compile time code generation is where we write code in the compiler so that the code can write code for us. And I'm going to show you a quick demo of what we can do with code generation. It's not a very useful example, and the code we're actually going to produce today is not very useful either. But it's hopefully it can trigger your minds and your imaginations to figure out what you can do with code generation further on. And then we're going to do some generating. We're going to talk about the history of how you could generate code in C# and what you can do today. And then we're going to showcase. We're going to make an implementation that generates an equals method and a get hash code method for a class. And then we have some wrap up after that. So let's see if the demo gods are with us today. So we have a simple C# program. We have a dependency on an open source library called JSON generator, I think. And what it does is it reads JSON from a string and generates a class based on the JSON it reads. So what we can see up here is we have some JSON up here, right? Just hard-coded JSON, and then we use that so they mirror each other, right? So what we do with code generation is that this class doesn't actually exist anywhere. It's only generated during compile time, so it only exists when the compiler runs. So what we can do is we start messing with the JSON up here. If we remove the name, you see it turns red. So now the user class has no name anymore. And we can add another attribute. We can add it back in. And you can see now it's there in the class again. So this is the power of compile time code generation, is that whatever we do something, we can make that reflect automatically in our code, in the code that produces the code that we use. So what can you do to achieve this? Well, prior to .NET 5, you had to use some sort of custom tooling to achieve this. In .NET 5, we got Roslyn source generators. And then in .NET 6 and after that, we have something called incremental source generators. And I'll explain what the difference is once we get there. But so before .NET 5, if you're stuck on anything prior to .NET 5, this is basically what you have to do. You have T4 text templates, which it's Microsoft, so it's XML. You have standalone tools, which can be whatever you want. You can write it in C# or Visual Basic, or you could write it in JavaScript or TypeScript or anything. It's just a standalone tool that you call, probably from an MS Build task that generates code. You would probably check it in. So you generate it once, you can generate the source code. You add it to your repository, and then when something changes, you need to regenerate. There's a question?
Yeah, so I don't know what you mean by custom tooling, but T4 it's built into Visual Studio, right?
Yeah. But it's not built into the compiler. And then we have something called code DOM, which I've never used. But it's a DOM in there, so it's probably XML, right? In .NET 5, we got Roslyn source generators. So Roslyn is, I don't actually know when Roslyn was launched, but it's analysis implementation in the C# compiler, where you can hook into the compiler, and you get an API where you can analyze the source syntax tree, and actually the semantic model as well, which is we're in a sort of a hybrid state between compiled code and source code, where we have access to a little bit of both. So you can analyze the source code, and you can do static analysis with this. You can detect patterns and anti-patterns, and you can warn the user about it. But what we got is, in .NET 5 at least, you can also use this to generate code. So you get access to the source code, the source tree, and the semantic model where you can resolve class hierarchies and all that. And we can generate code, and we can tell the C# compiler that I want you to compile this source code as well. We will add this in during the compilation. And this runs once. So you register a source code analyzer like this, and the C# compiler runs your source code generator. It gives you the source code, and it expects you to add source code to the compilation. It does it once. And once you do that, it's done. You can't see the source code that any other generators have generated. So you can't run a generator on, for example, the JSON class that was generated. You can't analyze that and then run a generator and generate something based on that. And it also runs through all source code every time. So every time you compile, it runs through your whole project, it gets all the source code, and it analyzes that. And in .NET 6, we've got something called an incremental source generation. And the main difference here is it's still executed by the compiler. You still have the Roslyn API to analyze the code with. But this only analyzes changed source code. So it differs in how you set this up. You set it up as a series of callbacks, and you have filters. So the compiler caches everything, and it sees that this source generator is interested in this part of code. So when that part of the code changes, it reruns your source analyzer. So if nothing changes in the parts of the code you're interested in, it doesn't run it. So the performance is much, much greater. And because it's incremental, it runs essentially until no more changes happen. So in this case, we can actually analyze source code that has been generated. So we can run the JSON class generator, and then we can run a source code generator that analyzes that generated class and generates new code or analyzes that code in some way. You can, if you're not careful, or maybe if you do silly stuff, you can make this run in an infinite loop, where it analyzes its own source code, produces more source code, analyzes that, produces more source code, analyzes that, and then you'll sit there waiting until, I guess, you run out of memory or something. So this is what I'm going to talk to you about today on show off, hopefully. And we're going to be generating an equals method and a get hash code method for an existing class. And I think this is one of the strengths with C# compile time generation, is that we can use partial classes to achieve this. In many other languages, you can just generate new classes because you can't inject code into existing classes. You can in Java, but that's a bug in the compiler. That's probably become a feature because it's been quite heavily abused. And I just want to say a quick note about marker attributes. If you saw this attribute on the JSON string, that's called a marker attribute. And we use that in source code generation to sort of tell the compiler which parts of the code we're interested in. You can just get all the classes or everything in the compilation, but that's a lot of source code to throw through. Using a marker annotation, which makes this kind of opt-in, you tell the compiler, I just want everything in the code that's annotated with this attribute. You get those parts. You get the incremental, you get the caching of everything that hasn't been annotated with this attribute. So performance is increased, and it's also opt-in, because otherwise you need some sort of filtering to determine what should I actually generate for. Because you get all kinds of classes in here, and you probably don't want to generate for everything in the source tree. So using marker attributes, as in this case, the JSON example, and they also have the string there that tells you what the class is going to be named. It gives you a point of configuration and a point of opt-in. So we're going to use that as well. This is implemented in an example solution because this is a specific generator. I'm not actually using this in a project. We're just doing the generator. So we have our CodeGen project, we have our tests project, and our integration test projects, and we'll see what the difference between them are later. The CodeGen project just uses the code analysis packages as dependencies, so we get access to all the source tree and all those models. The codegen tests depends on the codegen project. And then we have fluent assertions and XUnit, just to be able to write good tests. And the integration tests, this is where it differs. So the integration tests depends on the codegen package as an analyzer, which is we tell MS Build that this should run as an analyzer, not as a project dependency, but as an analyzer. And we do that by specifying this the dependency this way. So we include it as usual, and then we tell it that this is an analyzer, and we should not reference the output assembly, which means if this is set to true, you can access the generator classes from your code. So you can do, you can extend the generator, but that won't be a generator. So it gets kind of confusing. So set this to false, or you will have access to stuff you shouldn't have access to. It will still run as an analyzer because we told it is an analyzer, but it will also be available as a dependency. So the way I do live coding is I record everything beforehand, because then I don't need to remember all the weird classes I need to type. And I can also focus on talking about what happens. So this is a recorded implementation of an integration test, because that's where I like to start with source code generators. So we just create a test class up here, and we'll start adding a test. And of course, since it's an equal and hash code generator, we want to make sure that the equals method works as a good test. So we'll write a test for 2 equal instances should be considered equal. Quite fairly equal, fairly easy test, fairly basic, but also round trips the whole. We need to generate the code, and we need to make sure that we have a correct generation. So just some boilerplate setting up. We need a test subject record, or class in this case. It's partial, so we can generate another partial implementation that contains the equals method. And we just need some attributes that we can use for equality, a string and a number. And now we can add on our tests, which is we just check the equals method, right? And we make sure that they are equal. And we can run this to make sure it doesn't work, because we do test-driven development, right? And let's just add on the marker attribute as well, because we need that for opt-in. And now, so now we need the actual marker attribute, right? Because that doesn't exist anywhere. We get a compiler error because we don't have access to the equals and hash code marker attribute. So now comes the time where we need to decide how do we include this attribute in our solution or our project. And we have 3 different ways of doing this. So the first one is we could create a separate project, codegen API. We put our attribute in there, and then we can depend on this both from the codegen project and from the integration test project. We don't need it in the unit tests because that doesn't compile. You'll see that later, but that doesn't compile the actual class. Another way, I typically do this if I have more dependencies to add. If I have some interfaces or abstract implementations or stuff that I need to tack on anyways, then this works really well. The other way of doing it is we can just reference the output assembly that I told you about before. We set that to false. If we set it to true, we can depend on things in the analyzer project. So if we do this, we get access to the analyzer, but we can also put the attribute in the same package as the analyzer, and we can depend on them there. I don't like this method because it means that we have access to all the internals of the generator. So there is a third way, and we can just generate it. We are source code generators, so we can just generate the attribute during compile time. Super easy. If all you need is an attribute, this is what I do. So let's do that. Let's create our source generator and make it generate an attribute. So we'll go up to the CodeGen project. We'll create our equals and hash code generator. And this needs to extend the I incremental generator interface, because we are writing an incremental generator. We need to mark up with the generator attribute, so the compiler knows that they should actually run this as a generator. Marker attribute again. And now we have the initialize method, which is where we set everything up. So we will register initialization output here, and you can see this is a callback. Everything we do with source generators is callbacks because it needs to be cached. So we don't decide when this should run. The compiler decides when this should run. So what we do here is we register a pre-initialization, a post-initialization hook that adds some source to the compiler. And in this case, we add the attribute. So we name it equals and hashcode attribute. That's a file name hint. It needs to be unique, otherwise your analyzer will crash. And we just add some source text, which in this case will be hard-coded as an attribute on the class, or a constant even. So let's add the constant. And it's just a really, really simple attribute implementation. No bells and whistles. We can tell the compiler that this is auto-generated. I don't really know what that does, but it's all on all the other generated classes I've seen, so it seems good to add it there. And then we get to the actual attributes definition. There we have our attribute. And now we can rebuild the project. And it should actually build this time. And we should get yeah, it doesn't. So the problem here is, you see, we have generated it. We need to reboot the source generator. So the problem here is that the .NET compiler caches source generators quite aggressively. So if you have compiled with your source generator once, which we did before when we tried to run the test, it caches that version of the generator. And if you make any changes, it doesn't pick them up because it uses the cached version. So whatever we do changes here, we need to make sure that .NET ejects the cached version. And lately, you can do this in Writer if you press the button reboot source generator, reboot Roslyn source generators, and then rebuild. You should see that the now equals and hashcode turns blue. So this means that Writer has picked up our new source generator, but we can still see the build failing because the .NET compiler hasn't picked up our new source generator. So we need to make sure this, so they are not in sync here. Writer knows about our changes. The .NET compiler does not. The .NET compiler still doesn't know that this attribute exists in our generator. So just up until like a month or so ago, this was really tricky to achieve. You had to, the easiest way I found of doing this on Linux was to just pull up a terminal and kill all instances of .NET, because that would reboot the compiler, because then we'd throw away the cache. On Windows, because there runs a lot of .NET services on Windows, if you just kill all .NET services, your computer will complain. So I eventually had to reboot my system just to make this work. They have fixed something, so if you just rebuild the project from scratch, it picks up the new version. So it's a lot easier now rebuilding the project works, as we will see. Turns green. It's picked up our changed code generator. And that means that we now have the marker attribute. Everything compiles. So, but can we do this without rebuilding the project all the time? Because if you have in this case, it's fairly quick to rebuild a project. If you have a major solution where this is just a small part, it can take quite a while to rebuild the solution all the time. So what we can do is we can go to the unit tests, and if you want to iterate on something quickly, you get a simulator, right? If you want to learn to fly, you don't get in a plane, crash, burn, get a new plane, get in a simulator. So what we need is the Microsoft.NET compiler simulator, right? Luckily for us, Microsoft has already implemented this. There is a high amount of testability in the Roslyn source analyzer and generator code. It's not very ergonomical to use, but we can fix that with an extension method. So let's go into the unit test package or project, and let's add an extension method to the incremental generator interface that we can just use to push in some source code and get the generated files back. And then we can make assertions on the generated files. So let's make an extension class and a method. We want a dictionary that contains the file name and the source code mapping. And it should take the incremental source generator and a source code snippet. And what follows now is a lot of setting up all the things you need to run the incremental. You need a compilation, and you need a metadata provider, I think it is, that you push into a generated driver that then runs everything for you. I don't know if this is how the compiler does it internally, but this is what you do if you want to test these things. So we create a new compilation. We need an assembly name or a path. And then we add in some. If you want to reference, if you want to actually reference things in your source code here, because you can get compilation errors, you need to use .NET packages and add them here. Otherwise, you will get compilation errors in your compilation simulation. But for this small test we're doing, we just need the base assembly. So we just borrow the type of the assembly of the object class. You can see up there we also add the source code parsed as a syntax tree. And now we can run the compilation with the driver, and we can transform the result into a dictionary of file names and source codes. And you can see we have the file path of the generated file, and we have the source code. Make it into a string, and we have our extension method. So now we're ready to write our test. So let's write a unit test using this extension method. Add a new class, equals and hash code generator tests. I'll just write a simple test case that the question here is, what should we assert on? Because this is just synthetic, right? This doesn't produce any runnable code. So the only thing we have to assert on is the actual source code that the generator spits out. So we'll just need a basic source file that triggers anything, essentially, because since we always generate attribute, the input source code doesn't really matter as long as it's actually valid C#. But we can add on a test subject class. And the attribute. And then when we run the compilation or the generation, we should expect a file that contains the attribute definition. So two ways of asserting this is that we could assert that there is just a file generated. Quite simple. It doesn't tell us anything about whether that attribute actually works or not. So what we do is we get the results and we assert that it contains the file that we're looking for, and then we assert on the content of that file, so we know that it's actually generated an attribute and not something else weird that we're not interested in. So file paths for generate code always starts with the package, the project name, the package name, then the generator's name, and then whatever file name you provided as a hint. So you can't collide with other source generators files because they're always prefixed by the name of your, the namespace and the name of your code generator. And we can see here our marker attribute works. So we can add on and check the actual value of it. We'll get the source code, trim it, and we'll just make sure it matches what we expect it to be. And this is basically just a copy or paste of whatever we put into the source code of the generator. Get the attribute usage, and then we can get the attribute code after this. And we'll trim that just to make sure we don't get any white space issues. So now we can run our test. Hopefully it's green. I mean, since this is recorded, it would be embarrassing if it wasn't. And we can see here that while this works, if we change something, if we just make it an equals attribute, we get an error, which we should, because we changed the name of the attribute, right? Shouldn't work. But if we put that back and we just change something in the source code, we had a blank line in the middle. And you see here, we get this wonderful error here that tells us that something is wrong, and it tells us that the strings differ. And it probably just tells us that they differ, and then it's a new line. This isn't very useful. I mean, this is basically snapshot testing. You can see here. Differs near, new line, bracket. Now this, I mean, you can figure out what's wrong here because we only have one bracket like that. But if this is a long class, long definition with multiple blocks, multiple methods, how do you find the white space difference between your generator's output and the generated code? Well, by trial and error and lots of head scratching. So this is not a good user experience either. So we have really no good solution to how to test this. Both have severe drawbacks. So in the integration test case, we need to rebuild the project every time we change the source generator. But we do test the functionality. So we can change anything we want from the implementation as long as it actually passes the equals test. But then we have the unit tests where we can just develop as usual. Incremental compilation, run the test, change something, run the test, but you need to assert on the exact output. If you change a single character in the output, your test will fail. So given this, and that this project isn't that big, so actually rebuilding the project all the time is doable, we're going to continue with the integration test path. And once we have that, we can start actually generating the partial class that will implement our equals and hash code. And we do that by registering another callback. And this time we get a collection of the classes that we should act upon. So we get the syntax provider, and then we use this method called forAttribute with it's hidden. But we essentially tell it we want to have this attribute. So we give it the name of the attribute. There we go. If we can get Rider to not show all these things for us. So we tell it up here, behind this nice box, here we go, which attribute we're interested in, and then that class will filter out all the classes that are annotated with this attribute for us. We can add on an extra predicate. Here we go. forAttribute with metadata name. We give it the attribute. We can give it another predicate that can see further filter all the classes it finds with this attribute. If we want some more filters, we could maybe see here that they need to be partial. They can't be sealed, for example. And then we have a transform here, where in this case, we know that we can only have the attribute on classes, so we can just cast them to class declaration syntax. So now we get a list of classes. It isn't actually a list. It's an incremental values provider, but you can treat it essentially like a list. So we can do link stuff to it. We can do where. We just make sure it's non-null. It should never be null here, but can never be too safe, right? And then we collect it into a list or an incremental value provider, and we can combine it with the compilation provider, which gives us, so now what we get here is we get the compilation together with all the classes. And we can use that to get the semantic model of the code. We have the syntactic model of the code, and we have the semantic model of the code. So the syntactic model of the code, that's just a syntax. If you have inheritance, you see the tokens that make up. You see public, class, foo, and then you can see that it extends something. But you can't really resolve what something is. You can see the text that it resolves something. In the semantic model, we can see that this is a class. You can see the full hierarchy of what it extends. It resolves the namespaces, and you can actually go through and you can inspect the members and the functions of any parents in a hierarchy. And we need, for that, to go into the semantic, we need the compilation provider, because that's what provides us with the semantic model from a syntax tree. So we combine those, so we get the classes together with the compilation, and now we can register some source output. And here we get there you see we have the context. That's a context for the adding the source, and we have the pair, which contains the classes and the compilation. So now we can use the compilation together with the classes, and we can loop through each class, and we can generate the partial implementation containing equals and hash code. So I like to call out to a separate class just to keep everything contained nice and clean. So we'll just create a new implementation generator. We give it the class, we give it the context, and we give it the compilation. And that's all we need to be able to generate this. We generate some source code, and now we're ready to start generating this class. So when we generate this class, when we provide the implementation, we need to provide source code somehow. And this source code is dynamic. It needs to be generated by us. So there's a few ways of providing source code. One of them is this, which is the syntax factory way, where you essentially use syntax factory to create every syntactic element you can have in C# code. So this is an equals method, by the way, if you haven't figured that out. Can someone tell me what the bug in here is? There's not a bug in here. This produces perfectly compilable C# code, but there is a bug in the C# code it produces. The equals method implementation has a bug. I mean, this is not a big method. This is like 3 lines of code if you print it out. So what I don't like this. Yes, it's type safe, but it's also impossible to read. So I usually just go for string interpolation. So this is the same code. Can you tell me the bug now? Well, there's a null pointer exception in here. It's a lot easier to spot when you can see it like this. And if it gets more complex than this, I like to just pull in a templating engine and write, in this case, fluid liquid templates. Very readable, easy to use with, easy to work with. We've been doing templates since forever. But since we're doing this kind of code right now, we're going to stick with string templates. So we're ready to implement our implementation generator using string interpolation. So we just create a class and basically just fill in the blanks. I like to use this new style of constructors, which means less code to type. Generate the source code method. And what we do here is essentially we just generate the source code. I like to use attributes, so I'll just type in some string that contains all the source code we need. Essentially what we just saw in the example. And then we'll just backfill everything by implementing those attributes later on. So we'll have the namespace. We need the name of the class, of course. And we'll do the equals method. And in the equals method, we will need the name of all the attributes or properties in the class we're generating for, which is what we call member names. You can do lots of things with the members. We're only interested in the names of all the members. You can get the type and the class hierarchy of all of them when you have the semantic model. So we'll just do a quick, so we can call equals on an object that then calls into a type-specific equals method. No bugs, or at least no null pointer exceptions. And we'll just combine object.equals for all the members in this class. There we go. That's all the source code we want to generate. And we just need to fill in the class name, the namespace, and the name of all the members. So the namespace and class name are quite straightforward. The class name we can actually just get from the syntax, because that's a token in the definition, right? Public class or public partial class name. So that's really easy to get. We just get the identifier. A namespace. Here we actually need the semantic model, because this needs to be resolved, because this is not part of the class definition. This is something that comes before the class definition. So we need this semantic model. So we'll get the semantic model for the syntax tree of the class. We get the declared symbol of the class. So this is actually what the compiler knows about our class. And from there, we can cast it as a named type symbol, and which is just essentially just a class. And from the name type symbol, we can get the containing namespace. And from the containing namespace, we can get the name of the namespace. So now we have the class name and the namespace, and we just need the member names. Now, C#. Right. C# has multiple ways of including members that we might be interested in. So we'll get all the members of the class. And this includes all methods, constructors, properties, and attributes. We don't want the methods and the constructors. So we'll filter those out, and then we just need a name of them, right? So we'll call out the two methods. Should include member and get member names. So we have should include member, which takes a member declaration syntax. And in this case, we can just go if it's a field or if it's a property, then we're interested. This is essentially what we can do at this point. If you want more information about the field or property, you need to pull out the semantic model and resolve everything. So then you can analyze the types. Otherwise, you can just get the text of the type. You can't get the actual type and check type hierarchies and stuff. And to get the member name, we use an IEnumerable up here because in C# you can declare multiple variables on the multiple attributes on the same line. You can say string and then 3 identifiers. Gives you 3 attributes that are strings. And since we are in the syntactic model here, that's what we get. We don't get 3 different members. We get 1 member because it's declared as 1 member with 3 different names. So that's why we have an enumerable here. So we iterate, we get the declaration, we get the variable names, and then we get the ID of the variable, just to handle the case where you can define multiple variables of the same type on the same line. And now we have the member names. We're actually ready to test this out. But first, I want to talk about properties. So properties in C# can take many shapes. And these are the 3 ones I came up with. I think it's the most common ones I use. There might be more. But we have just an auto-generated property, which is just a public property with a getter and an initializer, which are auto-generated. These are backed by a hidden field, which is created at compile time. Then we have a custom backed field where we make our own private field, and then we have a initializer with some guards in it, and then just a simple getter that returns it. And then we have this down here, which isn't backed by anything. This is just a calculated property with a getter. In this case, it's a shorthand syntax for a getter. I would say, if we're trying to be smart, we just want the top property, right? In our equals method. Because we will get the private int age. That's an attribute. So we will get that in our equals method. So we don't need the age with a capital A in our equals method, because that's the same. And we don't need this here either, because that's also derived from the age. So if we're trying to be smart here, we have the syntax I wrote up there. If we split this into a switch, we always want the fields. We always want the fields, but we can do stuff with the property. So if we look down here, now this has no accessors. And accessors is get set init. Since we declare it like this, the accessor list is null. So if the accessor list is null, we don't want it. So we only want it if the accessor list is not null. If we look up here, this has an accessor list because we tell it we should have the get accessor and the init accessor. But they have no body. Because we haven't specified them, they're auto-generated, they have no body. If we move on to here, we have our field. And then we have two accessors with bodies. And we don't want to include them. So in this case, the field is always included. We want that. We don't want these. But this will include them because we have accessors, right? So we need to check if the body is null or not. So we go through and we check if there are accessors and all accessors have a null body, then we want to include this. And if we combine that with that it should be null as well, no accessor list, we get this switch up here, which is a bit difficult to reason about maybe, because we have, if the accessor list is not null and all accessors is null, then it's true, otherwise it defaults to false. I think the better solution actually is to just use a marker attribute again. Make it opt out. We can in our code just see, is there a marker, is there an attribute on this? Well, don't include it. That's how we can filter it easily. That means that the developer using our code can just choose it. So again, marker attributes makes stuff easier. So with this, we have our implementation. We can rebuild our solution, and hopefully we will have a green test. And in this case, we're testing the actual implementation of the equals method. We are free to change that without breaking our test case. Awesome. We can add on some more tests. I think we're not going to do that actually because we're running out of time. We can generate our hash codes. Now there are a few ways of generating hash codes. If you search the internet, you might find that one up there. That's an answer by John Skeet on Stack Overflow. It's taken from a book, which I don't remember who wrote it. You can do it like this, which is the recommended way if you have lots of attributes. I think hashcode does that up there actually internally. It ends up doing something like that. Or we can just do hashcode.combine if we're lazy. This works for up to 8 attributes. So we can just generate this method. And we just use hashcode.combine and we use the member names. Because we're lazy. So this won't work for classes with more than 8 attributes. But that's, I guess, future development. There we go. There we have a complete implementation of a hashcode equals and hashcode generator. So to sum it up, Roslyn incremental source generator because they're more efficient, faster. We use marker attributes to decide what to include and not include. I prefer using integration testing when I can, because unit testing gets really, really specific. It's really brittle. And I do prefer string interpolation or templating over the syntax factory because it actually means you can read the implementation of whatever you're trying to generate. And we talked a bit about techniques for the property selection. So what can you do with this? I hope you have ideas. I usually think of this when I'm in an actual problem. It's hard to brainstorm about, okay, I have a tool, what should I use the tool for? But I've done automatic dependency injection modules, where you just mark your classes with something and it creates an extension method where you can just call it on your DI container. Flavor generation of test cases, where we tested 3 different database engines. We had one abstract test case, and we just generated concrete classes that injected the database fixture of each type. So when we added the 4th database flavor, we got some 1,200 new test cases by just adding 4 lines of code in our generator. That was a good day. You can do really performance serialization instead of using reflection in runtime. You can just generate the serialization, so it gets statically generated. And you have a code. You have actual code that does your serialization for you. Aspect-oriented programming. You can add stuff like logging to this. You can annotate. Sadly, you can't transform existing methods. You can just add on functionality. You can't transform source code. But you can add attributes for logging and inject them into your code. You can generate companion code if you have a companion object to something. You can generate that based on the object you have or the class you have. And you can read a domain-specific language and generate that into code. We are looking towards doing that for domain-driven design at the moment at Factor 10. Trying to describe our domain model in a DSL and then just have the model generated for us. So we don't need to keep them in sync. I do have some bonus stuff. I realize we are over time already. But one thing that doesn't work with this for attribute with metadata name, that's aliasing. So if you would try to do something like this, because it looks for the codegen.equals and hashcode attribute verbatim, right? So if you alias it, you won't find it. In that case, you need to have your filter later when you have access to the semantic model, in which case it will resolve EQ to codegen.equals and hashcode attribute. And something that might make unit testing viable is, I've just toyed a bit with this. I haven't made something that's really useful, but it looks promising. If you provide the entire .NET SDK in your compiler simulator driver, you can actually make it produce an assembly. And you can load stuff from the assembly using a reflection. And then you can use dynamic to call methods on the objects that you created from your assembly. So given there's a lot of setup above here, if you get that set up right, you can actually call the generator from a unit test and then run the generated source code in your test. So you can get basically the best of both worlds. You get the fast iteration from a unit test, but you're also checking functionality and not syntax of the source output. All right, I'm done. Thank you.